Good morning and welcome. We are in section 622 today, and the title is How Can I Solve the System? So we are continuing our discussion of solving systems of equations. We're going to start by reviewing what we did yesterday and solve this system. I encourage you to uh, pause the video and solve this, and then check your work. Um, Maybe before you pause, one of the things we talked about yesterday is the equal values method. And if you can get to a situation where an expression or two different expressions are equal to the same thing, then they have to be equal to each other. So thinking about this for this particular problem, I would probably take this second equation and rewrite it as so that y was alone. So I could change it to 5y is equal to negative 3x minus 13. And I can see as I look across there are three different terms, and I'm going to divide all of those terms by 5. So this is going to become y equals negative 3 fifths x minus 13 fifths. So we can see each of the three terms were divided by 5. At this point, what's nice is this negative 3 fifths x minus 13 fifths is equal to y, but also y is equal to the opposite of x minus 7. So since y is equal to y, we can take these equal values, right, and set them equal. They are equal values. They're equal to each other. So we can set the expression the opposite of x minus 5 equal to negative 3 fifths x minus 13 fifths. And from last semester, you know I'm inclined to eliminate fractions where possible. So I can see that I have these fractions that have denominators of 5. So I know that if I multiply this entire equation across by 5, it'll be gone. So I'm going to hit every single term with a factor of 5. So this equation will change to negative 5x minus 35 equals negative 3x minus 13. And I think you can see that's much better to deal with. That looks way better. Let's go ahead and add 5x to each side. So this will become negative 35 equals, if I add 5x to this side, it's going to be a positive 2x minus 13. I'm going to add 13 to each side. And when I do that, I get on this side negative 22. And that will equal positive 2x. And when we divide both sides by 2, we get negative 22 over 2 is x. Therefore, x is equal to negative 11. So that's part of my solution. Right? X is negative 11. But I need to figure out what y is. And I am going to use that first equation up at the top. I'm going to use y is equal to the opposite of what x is, minus 7. And in for x, right, I'm going to place the value of x that I found, negative 11, into that. So I get that y is 11 minus 7. Therefore, y is equal to 4. And at this point, I claim, I believe I have a solution to the system. I'm going to write it as an ordered pair. X is negative 11, y is 4. And just visually here, I'm going to check this in the second equation. I'm going to go 5 times 4 is 20. And then that's going to be 20 minus 33. Yeah, that clearly, 20 minus 33 is negative 13. So it works in the second equation. And I think it works in the first because that's how I figured out what y was. But let's see, the opposite of negative 11 is 11, and 11 minus 7 is 4. So it definitely works in both equations. So this is our solution. We are going to outline a different technique for solving a system. The technique we looked at yesterday is great, particularly if you already have one of the variables isolated and you can set the equal values equal to each other. But um, I want you to just write down in your notes this word substitution method, and what follows below is a demonstration of how the substitution method works. So I'm going to show you how to solve the same system using substitution. And one of the benefits of using substitution is you never go through this step where you have to deal with fractions. And I mean, if I'm honest, the fractions are not particularly bad, right? It's literally one step multiplying by 5 and the fractions are gone, but it is a benefit of the substitution method. So let's look at the exact same problem, but this time in your notes you're going to write down we're going to do this with substitution. And if you look, the idea is this. In the very first equation, I have an expression that equals y, right? Y is the opposite of x minus 7. In the second equation, I have a location that requires a y value right there. And what I'm going to do is rewrite the second equation using the expression that's equivalent to y from the first equation. So if this is perfectly set up for substitution, so we'll use that. And if you look at the work follows like this, this is going to become 5 times the quantity of the opposite of x minus 7 plus 3x equals negative 13. So just careful inspection. All that I've done is I've taken what is y from the first equation and I've replaced y in the second equation with that expression. The benefit is now I have just the one equation with only the variable x. The next thing that I would do is distribute this value of 5, so this is going to become negative 5x minus 35 plus 3x equals negative 13. If I combine my like terms, I'm looking at negative 2x minus 35 equals negative 13. If I add 35 to both sides, this is negative 2x equals, oh, I'm embarrassed. I actually know the number, but I'm grabbing a calculator. And of course, the reason why I know the number is I literally just did this above, except it was positive. So this is going to be, it was negative before, this is going to be negative 22. And then when I divide both sides by negative 2, I get x is negative 11, which is exactly the value that we got for x in the previous method, right, using the equal values method. And then as a final step, again, and I'll just write it here to include it, I would use this equation for y, and I would write that y is equal to the opposite of x, which is negative 11, and then minus 7. So we're looking still at 11 minus 7. Y is equal to positive 4. So as we zoom out and take a look at this, we see that we have, in both cases, right, well, that's a mess. In both cases, we ended up with the exact same value for x and y, negative 11, 4. It's just we use this technique we're going to call substitution. And I want you to be able to, as we're working through, be thinking about, especially as we proceed and we learn even more techniques, be thinking about, what's the best method? So right now we have 2, and it appears that substitution, right, is great if you have one of the variables isolated in one of the equations and you can replace that in the other. So this was well suited for substitution. Let's move on to question 57. But before we look at that, I'd like to look at question 50 from last night's homework and make sure we understand this. So Jonathan and Laura are 3 miles apart. and traveling towards each other. Okay, so we have two people. I'll say that this is Jonathan and this is Laura. And the total distance between them is 3 miles. And they are traveling towards each other. If Jonathan travels m miles, so I don't know how far that is. I could put an x literally anywhere. I could put it here, here, here. I don't know where he's at precisely, but I'm just going to say if he were to travel, let's say, m of the miles, right? So if he travels a distance of m miles, the question we're asked is write an expression to represent how far Laura has traveled when they meet each other. So we can see that the distance she's going to travel is it's here. I'll highlight it in this green color. So she's going to travel this distance. But the question is, what's an expression that represents how far she has to travel? And you can see I do not need to introduce a new variable, right? I'm not going to say, well, she's traveled n. I'm going to use the two things I have and write an expression using that. Well, the total distance is 3 miles, and if I take away from that the distance that Jonathan travels, which is m, I get an expression that represents how much she traveled. And so her distance right here from here to here is going to be 3 minus m miles. So whatever Jonathan didn't travel, she's going to travel. And I know this is right for a couple of reasons, but primarily I know that it's right because if I take m, the distance Jonathan travels, and I add to that the 3 minus m that Laura traveled, right? When I add those together, I get that the sum is 3, which is what it should be. So I want you to think about this as we look at this next problem. So this is what we're presented with. Bharat and Ingrid leave their building at the same time on their bikes and travel in opposite directions. If Bharat's speed is 12 kilometers per hour and Ingrid's speed is 14 kilometers per hour, how long will it take until they are 78 kilometers apart? So let's try and create a brief sketch here and maybe a table to summarize this information. So in my sketch, I'm going to say that they're starting at this central point. It's the building that they're starting at. And I'm going to say that just arbitrarily that Bharat's going to the left. And I'm going to say that, so this is Bharat. That's his location. And Ingrid is going to the right. And I'll just put a capital I there for Ingrid. The other thing that I'm going to do is, let's see, I'm going to, it says right, well, let me create this table that I'm fond of that I showed you yesterday in class. So I know that two quantities they're traveling, and that both of these will have a distance that they travel, the rate at which they're traveling, and the time that they spend traveling. And I'm going to say that the top one is Bharat, Bharat, and the bottom one is Ingrid. And the distance, well, the distance is the difficult part slightly, but I want you to look at part A. It says, hey, if Bharat rides a distance of b kilometers, so if he rides a distance of b, write an expression to represent how far Ingrid rides. So think about this. They're riding in opposite directions, and when they're done, we know that they're going to be 78 kilometers apart, right? So they're going to be 78 apart. So if Bharat traveled b of those, that means that Ingrid would have to travel the rest. In other words, she would have to travel the 78 minus what Bharat traveled. So the total distance, 78, minus what Bharat traveled, is exactly this distance right here that Ingrid has to travel. So that expression, it represents his distance. Now, the other thing that's happening here is we do have a speed for each of them. We know that Bharat is traveling at 12 and his speed is expressed in kilometers per hour. And Ingrid's speed is 14, and her speed is expressed in kilometers per hour. And the other thing that we know is that as they travel, they're going to be exactly the same time apart. At the same time, they'll be 78 kilometers apart. So t is going to be the same for each one of these. The t is going to be equal. It's going to take them, because at some specific time, they're both going to be 78 kilometers apart from each other. Not 78 from the school, but 78 apart from each other. So B asks us to write in two equations and solve the system using substitution. So if I come back up here and I write this, from the first equation, remember the relationship between distance, rate, and time. Distance traveled equals rate traveled times time, and we got that from dimensional analysis over the last 2 days. But I can say that Bharat's distance, B, equals his speed, 12, times t. And for Ingrid, her distance traveled, which is 78 minus b, is going to equal 14 times t. And again, all I'm doing is I'm taking the box from distance, and that's going to equal the rate times the time, and I'm doing it for each. The distance, 78 minus b, is equal to the rate of 14 times t. Now that I have this isolated, it's very clear that a substitution would be well suited for this problem, because in the first box, right, this expression is equivalent to b, right? B is equal to 12t, and I can replace b in the second equation with that. So this second equation is going to become 78 minus 12t. And I could use parentheses, but it's not necessary because this is just one term. So 78 minus 12t equals 14t. If I add 12t to both sides, I get that 78 is equal to 26t. And if I divide both sides by 26, we get 78 over 26 is equal to t, which is precisely the number 3. So time is 3. So they're not, I think this problem just asked me, it said, the question was, how long will it take until they are 78 kilometers apart? So I know the answer already is 3 hours. So it will take, in 3 hours, they will be 78 kilometers apart. And that is my answer for this, 3 hours. If they asked how far did Bharat travel and how far did Ingrid travel, I could figure that out by calculating B would have to be 36, right? So I know Bharat traveled 36 and Ingrid traveled 78 minus 36, but that wasn't the question. The question was just how long would it take for that to happen. When we solved the system of equations below, she got the solution x is 1 and y is 6. Without solving the system yourself, can you tell her whether this solution is correct? How do you know? Okay, so she has this ordered pair where x is the number 1 and y is the number 6. And it's a great highly recommended technique. Once you have a solution, check it and make sure it works. If I take and I plug that into the first equation, this is going to become, when this is for x is 1, this is going to become 4 times 1 plus 3 times 6. 3 times 6 is 18. And 18, 19, 20, 21, 22, and 18 plus 4 is 22. So this works, right? This works. Congratulations. Um, but oftentimes, right, remember there's an infinite number of solutions for that first equation. So it could be the case that we just found a point that's on the first line but not the second. So it's always important to check it with both, because a solution to a system must satisfy both equations. And when I plug this into the second equation, it's going to become x is 1 minus 2 times 6. I'm suspicious, because it turns out that 1 minus 12 is a lot of things, but it's not 0. So because 1 6 does not satisfy the second equation, right? Because 1 minus 12 is negative 11 and not 0. 1 6 is not a solution. So we can tell me nope, this is not a solution. And I didn't need to do the problem. I could just check her solution and see that it was incorrect. Happy birthday! Hey, you have decided to give your best friend a bag of red and green marbles for his birthday. And good for you. Why not? I know we're in high school, but marbles are still cool. There's a lot of beautiful marbles. Your friend likes green marbles better than red ones, so the bag has twice as many green marbles as red. The label on the bag says it contains a total of 84 marbles. How many green marbles are in the bag? Write a system of equations for this problem, then solve the system. Using any method you like. Be sure to check your solution. Okay, mission accepted. I'm going to have a let statement. Let G equal the number of green marbles, and let R equal the number of red marbles. And I know that the number of green marbles plus the number of red marbles has to equal 84 marbles. And the other thing that I know is that the bag has twice as many green marbles as red marbles. So the number of green marbles is twice the number of red marbles. So this second equation is one that I remember contemplating way more than I should. I remember thinking about these a lot, but as I look at that, I write it down. I'm like, okay, did I get that backwards? And then what I would always do is say, okay, if I had 5 reds, if I had 5 red marbles, 2 times 5 is 10. Yes, this is the correct expression. The number of green marbles is twice the number of red marbles. Because it's possible you could have written this the other way. You could have said, hey, the number of reds, because I want 2 times the green, right? Well, that's not what this says. This is not twice as many greens. Actually, this is half the greens. And if you just plug a number in, like, hey, if green marbles was 5, red would be 10. Well, that's not what we wanted. We wanted the bag to have twice as many reds. So you can write down what you think is it based on and then just kind of check and say, hey, does that make sense? Does that feel right? And I think we're good here. Well, setting this up and solving it, right, it's pretty clear to me that I'm going to use substitution. Yay, substitution. Because the second equation has this expression 2r, which is equivalent to g. So I'm going to replace g in the first equation with 2r, right? I'm going to replace g with 2r. So this first equation is going to become 2r, which is the g, plus r, which is the number of red marbles, equals 84. So that means that 3r equals 84. And if I divide both sides by 3, I'm very pleased that it goes in evenly and gives me that r is going to equal 84 over 3, which is the number 28. So there are 28 red marbles, and I know that the number of green marbles is double that, so the number of green marbles is 2 times 28, which is 56. So my solution is, and it's important to write these down in English. If I don't do this, remind me. But the bag has 28 red marbles, or I wrote the bag has 28 red and 56 green marbles. So this is true if two things are true, right? We have the correct solution if two things are true. If I add 56 and 28, and I'm doing that on my calculator, I should get 84, and I do. So I can see that it definitely satisfies the first equation. And then for the second equation, if I take the number of reds, 28, and I double it, I should get the number of greens, 56. That works as well. So not only have I interpreted all of the words, I've come up with a system, but I can see that my solution satisfies the original equation. All right, and we're looking at our final problem today, question 60. Carter walked for a while at 3 miles per hour and then continued his journey on bus, traveling 15 miles per hour. His time on the bus was twice as long as his time walking. How long did he ride the bus? How long did he ride on the bus if the total distance covered was 66 miles? Let t equal the time he walked in hours. Well, that's nice that they're providing me with my let statement here. So let's see if we can't create an image that represents this. So this dot is going to represent Carter when he starts, and we know that he travels two different ways. For a while, he is walking. For a while, he's walking, and he is walking at a certain speed that they tell me. So we've got his walk. Then, from that point, he gets on some slow-moving bus. Very slow-moving bus. The bus is going 15 miles per hour. That's crazy. So he gets on a very slow-moving bus. My bicycle literally goes faster than this. So part of his journey then is on a bus. Now I know something. I know that the total distance that he travels, right, the total distance that he travels is going to be 66 miles. And he's going this direction. And I also know some different speeds here. So I think what I want to do now is create a table. Maybe this is helpful. Maybe my table's not helpful today. I don't know. So let's see. We've got the walk part of the journey, and then we've got the bus part of the journey. For the walk, we're going at 3 miles per hour. And for the bus portion, a very slow moving bus, 15 miles per hour. Even school buses go faster than that. There is a distance, there is the rate, we have it, and there is a time. And it says let t equal the time he walked. So this t is going to be how long he walked. And I feel like I'm missing a detail, so let me read this again. Carter walked for a while at 3 miles per hour and then continued his journey on a bus traveling at 15 miles per hour. His time on the bus was twice as long as his time walking. Oh, okay. So if he walked for t hours, then that means that he was on the bus for twice that, 2t hours. I think we're good. Are we good? Are we good? Because I have another issue here with the total of 66 miles is the total distance traveled. I haven't made use of that yet. I do know that if I add those two distances up, I'm going to get 66. Maybe I can do this. Maybe I can say, if I could be complicating this, if he walked a distance of d, if the distance he walked was d, then the rest of that was on the bus. So I could say the rest of it would be 66 minus d. So my thinking there is, if he walked for 6 miles, then he was on the bus for 60 miles, right? Because it says, how long did he ride on the bus if the total distance he covered was 66 miles? I think this works, right? If I think this works, let's write the system and see if this makes sense. So again, we're using the fact that when I multiply a distance in miles per hour, if I take a rate of miles per hour and multiply that by hours, I get distance. So that distance is the rate times the time. Miles per hour times a certain number of hours, right, is going to give me miles. So this is right. So one equation I could write is d equals 3 times t. Okay. The other one I can write is 66 minus d is equal to 15 times 2t. All right, that makes sense, right? Distance is rate times time, and I did that for both. So let's try and solve this system and see where it takes us. Oh, I am definitely going to use my new friend of substitution, because 3t is the same as d. So I'm going to place 3t right there. And this substitution is going to allow me to rewrite the second equation so it only has t's. So this is going to become 66 minus 3t is equal to 30t, right? 15 times 2. If I take away 3t from both sides, I get that 66 is equal to, what is it, it's 27t. And then 66 divided by 27 would equal t. And I'm embarrassed to say, but I am grabbing a calculator here. 66 divided by 27 is 2.4 repeated. So t is approximately 2.4 hours. But if I'm going to turn that back into a fraction, math, it reduces to, oh my gosh, I need my glasses. I think it's 22 ninths. 22 divided by 9. Yeah. So it is 22 ninths, or about 2.4 hours. So my only concern here is, like, if I use that value, does it really get me 66 miles? If I plug in t, if I plug in t to here, right, 3 times that t, and then 15 times that 2t, when I add those together, does it equal 66 miles? If it does, I've got it. So I am going to check that. I'm going to go ahead and go 3 times 22 ninths. So that's the distance he traveled on the bus. And then plus, I'm going to go 30, right, which is 15 times 2, and then times t, 22 ninths. Now, if this equals 66, then we've reached happiness. So I think I could do this on my calculator real quickly. So I'm going to go 3 times that number, and then I'm going to go plus 30 times that number. And when I do it, I do not get 66. So I am sad to say that this is not happiness. There's sadness here. And I bet if you're sitting at home, you see the error, and you probably saw the error I made quite a while ago, and you're like, stop, stop, stop. And the problem is this. way back here, this is where I went wrong. I was supposed to add 3t to both sides, wasn't I? hmm And that should have been 33t. Well, I didn't add the same thing to both sides. What I did was literally on one side I added 3t, and on the other side I subtracted 3t. I added 3t on the left hand side and I subtracted 3t on the right hand side. So let's try this by adding 3t to both sides. If I do that correctly, right, using the addition property of equality, not something I make up, I'm going to get 66 is equal to 33t. And even I know that 66 divided by 33 is 2. So I would say that t is 2 hours. Same check as before. If I take 3 times the 2 and I add to that the distance on the bus, which would be 15 times 2 times another 2. So what you can see as I'm going 15 miles per hour times 2t. If I do that, I should get a total distance of 66. So this is 6 plus 30 plus, yeah, so I do get 66 miles traveled here. So he was on the bus for 2 hours. Now, I don't know if that's what the question was. It says, how long did he ride on the bus if the total distance he covered was 66 miles? Well, if the question is how long he was on the bus, right? Well, t is how long he was walking. So 2t is how long he was on the bus. So the answer to this is what does it say? It says how long he rode the bus. He rode the bus for 4 hours. Well, thanks for hanging out. I hope you have a great day. And that's about the amount of time that we would spend in a classroom. So that was a fairly lengthy walk through some problems here. I'll be online as always. Join the class if you'd like to discuss anything you saw here today. I hope you have a great day, and I look forward to seeing you in class and online soon.